Welcome. In this session in linear data analysis, we'll state the singular value decomposition theorem. We won't prove it, but we will try to use it to explain some of the results of the other sessions in this lecture. So the singular value decomposition, a decomposition is a way of representing a matrix as products of factors, and these are sometimes referred, because it's composed of these factors, we sometimes refer to this as a decomposition. We'll sometimes refer to it as a factorization also. If we have a matrix A that has all real entries and it has m rows and n columns, then this important theorem says that A can be factored as a product of three matrices. One of them is referred to as U, one of them is referred to as V, and then a new one is sigma. And sigma is the Greek letter pronounced S, and that's for the singular values. A particular application of it is if A is a real matrix of this size, then U will be a square matrix, have all real numbers, and it will be an orthogonal matrix, which means that its columns are an orthonormal basis for all vectors of size m, and the matrix is, the transpose of this matrix is its inverse. The matrix V will be square, it will be all real entries, and it will also be an orthogonal matrix. So this matrix has orthonormal columns, and those columns are a basis for vectors that have n entries. And the new matrix, sigma, will be all real numbers, and it will have the same number of rows and columns as the original matrix A has. And this is going to be we put this in quotes, it's a sort of diagonal matrix. And the reason is, if A is not squared, then we can't have a true diagonal matrix. It means that we'll have a block of zeros down at the bottom or a block of zeros over on the right. But mostly we'll be interested in the diagonal entries. And the properties that sigma has is every entry on the diagonal is a real number. If the rank of the original matrix is R, then every singular value less than or equal to R is a strictly positive real number, and the values can be ordered as the first singular value is greater than or equal to the second, and so on, up until the singular value R for rank R, and after that all of the singular value entries are 0. The structure of this, so let's remember this, is that the structure of the singular value matrix is it's all real entries, and it has the same number of rows and columns as the original matrix A has. And this is its structure. So this is the most general case, where we start at singular value 1, which is greater than or equal to singular value 2, and so on, until we get to singular value R for rank R, and after that they're all zeros. And then as needed, we may have zeros on the right part, and we may have zeros on the bottom part. And these cases are represented here, and they handle the situation in which the original matrix A is rank deficient, and in one case it has more rows than columns, and in the other case it has more columns than rows. So let's now pause and let's take some examples and work through them. So let's take this example that we've been using throughout this lecture, and that was the matrix A that has its first column is 1, -1, 1, and the second column is 1, 1, 1. And for this, the SVD of A is orthogonal matrix U, singular matrix sigma, and orthogonal matrix, and it's always V transpose. And now let's observe that So we'll make these observations. U is the same as in B sub U, which was the right transpose matrix. V is the same as in BV, which was the left transpose matrix. And sigma has to have the same shape as A, which means it has to have 3 rows and 2 columns, and the singular values are 2 square root of 2, and then the rest of the matrix is 0. And now we can see the structure of this is it's padded on the bottom with zeros so that sigma still has the same shape as A. Can you recall what the eigenvalues of B sub V were? Well, they were 4 and 2. And sigma is the square root of 4 and 2. Can you recall the eigenvalues for B sub U? Well, those were 4, 2, and 0. And here we have square root of 4, square root of 2. And that is a general result. So we won't prove the SVD. For those who are interested, by the way, the SVD also works if A has complex entries. And instead of orthogonal matrices, we have what are called unitary matrices, but that's for a subsequent course. So let's use the singular value decomposition and let's explore these transposes. Let's take the left transpose, which is the one that we introduced first. So A transpose A, well, using the singular value decomposition, I can now expand. So A transpose is U sigma V transpose, and that whole thing is transposed, and then A is U sigma V transpose, and that equals, so when I apply the transpose rule is we reverse the order of things and transpose them, transpose each entry. So V transpose is V. Sigma transpose is, we'll write that as sigma transpose. We can't write that as sigma because sigma might not be a square matrix. So that's why we put the diagonal in quotes, is that it's a sort of diagonal matrix. So then we have U transpose, and then we have sigma, and we have V transpose. And now that equals, well, oh, I missed a U. So U transpose U is the identity, and sigma transpose sigma, we can write that as a square matrix sigma squared. So that will be V times sigma squared times V transpose. And that is the spectral decomposition of a symmetric matrix, and sigma squared is the eigenvalue matrix, and so the square of the entries in the singular matrix are the eigenvalues of A transpose A. Let's now explore the other transpose product. So A transpose, and likewise this will be, now we have U sigma V transpose times U sigma V transpose, all transposed, and that will be, now we'll use the associative property of matrix multiplication and get rid of all of the bracketing, and so that will be U sigma V transpose times, and when I transpose that, V transpose transpose is V, and then this will be sigma transpose, and that will be U transpose, and that will equal, so now V transpose V is the identity because V is an orthogonal matrix. This will be sigma transpose, so I'll write that U, and it will be this will be sigma squared U transpose, and that is the spectral decomposition of a symmetric matrix. Sigma squared are the eigenvalues, because sigma squared has to be all non-negative. That means that this matrix is symmetric and positive semi-definite. So once again, the entries of this have to be all greater than or equal to 0, and these are going to have shared eigenvalues, and the eigenvalues of this and the eigenvalues of this matrix and the eigenvalues of this matrix will be the same, except for in one of these cases there will be additional zeros, and all of the non-zero values will be real and strictly greater than 0. Now let's summarize what we've learned in this lecture. We're now able to state the dimensions of the left and right singular matrices from the size of a matrix that has real entries. We can write the structure of the singular matrix knowing the rank R of that matrix. And we're able to compute the eigenvalues of the left transpose and the right transpose of a given matrix A that may be rectangular. We can compute the singular values from these eigenvalues by taking square roots.